Hi, welcome back. It is now time for Chapter 5. There are two sections in Chapter 5. In Section 5.1, the first section, we're going to take a look at something called probability distributions. So let's go ahead and get started. We have three major concepts, three key concepts in idea. The first one is the concept of a random variable and how that relates to the concept of probability and specifically the probability distribution. We're going to take a look at if you were to take this probability distribution thing and graph it, what kind of graph you would get, most likely a probability histogram. And then we'll take a look at how to find parameters. Okay, remember parameters? Those are population measurements. The mean of a population is a parameter. The standard deviation of a population is a parameter. Okay? So population parameters of the mean, the standard deviation, the variance for that probability distribution. Okay? I want to point out that we're using this word here because we're finding those values for the entire population. These are not statistics of a sample, population parameters. Okay? And then we'll take a look at probably one of the most important things in here, this idea of whether outcomes for an experiment are significant. And this time we're going to look at that mathematical way to determine it. So we're going to look at things that are either significantly low outcomes or significantly high outcomes. All right, so let's go ahead and get started. All right, so here's our basic concepts that we have to internalize. So those basic ideas. First off, what is a random variable? Well, by definition, a random variable is a variable that has a numerical value for every outcome of a procedure or an experiment. Okay? So what we're going to do is we're going to take those things that we did before, where we had an experiment, and let's say our experiment was flip a coin. Now before we would have said that the sample space was the coin will land heads or the coin will land tails. Now to talk about finding a probability distribution for the experiment, flipping a coin, we can no longer have outcomes that are heads and tails. We have to assign a random variable that'll put a number on each of those outcomes. So we would say something like this. The random variable x is going to be the number of heads. Okay? So that means that my sample space now turns into 1, 0. The 1 being that when the coin lands heads, that's 1 head. So that would have a numerical value, a single numerical value of a 1. And when the coin landed on tails, well, that's not a head. So our count, our random variable, this counting heads, would have a count of 0. So then our two possible outcomes for the experiment were heads, 1, tails, 0. So a random variable takes an experiment, looks at the outcomes, and says, how can we define a variable that'll give all of these outcomes a unique numerical value? Right? Now, when we get all of those outcomes together, we can make something called a probability distribution. And what a probability distribution is it's a way to describe all of the values of the random variable. Right? And when I say describe those, you could describe it by making it a table. You could assign an algebraic formula to it, or you could make some sort of a graph that would describe those outcomes. Right? Now, the reason there's a bunch of different ways to do it is because, generally speaking, there are two types of random variables. There are our discrete random variables, and there are continuous random variables. Now, mathematically, when I see the word discrete, I understand what that means, but it's a tricky one, okay? Because a discrete random variable has a collection of values that is finite or countable, okay? Now, sometimes people struggle with those two words. Like finite, not a big deal. Like our example from before, the values for the random variable were 0 and 1. 0 meaning no heads, so the coin landed on tails. 1 meaning the coin landed on heads. That's definitely a finite collection of values. But what if we changed the experiment and said, hey, flip the coin until you get heads, right? Well, theoretically, I could flip a coin and it could land tails every single time. It would be highly unlikely for that to occur, but I could do it. So my sample space wouldn't be something simple like this. My sample space would be something like a 1, which means that I put the coin and it landed on heads the first try, or a 2, which means I flipped the coin and it landed on heads on the second try, or a 3, which means I flipped the coin and I didn't get a heads appearing until I flipped it 3 times, or 4 times, or 5 times. And mathematically, technically, we could argue that this goes on forever, right? We say in math that things like this, while they are not finite, they are countable, right? That even though there's an infinite number of them, they could be counted, I guess, if you had a really, really long time. Okay, now if you don't like that, it might be a little more clear when we take a look at the second one. A continuous random variable, by contrast, a continuous random variable, by definition, has infinitely uncountable measures in its for its random variable. Okay? So suppose that we had an experiment. Here's the experiment. The experiment is to time the sales call at the call center. So you got a job at the call center. It's not the best job you've ever had, but it pays the bills. People call in to complain about something, ask for help, or whatever they do at a call center. And what we're going to do is we're going to measure how long that call could take. Well, by definition, my sample space is going to be the interval from 0 to 24. And these are measured in hours. Okay. Because a phone call could last, and I'm putting 24 in there because I'm thinking of this experiment to be in a day. Like, how long could a phone call actually take in a day? It can take up to 24 hours before it's 2 days, right? And so our sample space is an interval. But if you think back to like algebra, when we talked about intervals, if we think of this as a number line, right? Over here we got 0. Over here I've got 24. I want to have the interval from 0 to 24. So I want everything possible in between there. And how many values are in between there? Well, if I had an accurate enough measuring device, a timer of some sort, there's so many numbers in there. There are infinitely many of them, and I can't even count them, right? Like up here, this was infinity, but I always knew what number was coming next. Like I knew after 5 came 6, and I knew after 6 came 7, right? Because there's a pattern there. So that's what makes it infinite but countable. The reason that this is not countable, right, which is right here, the reason that this example down here is not countable is if I had a phone call that took 0.43 hours to deal with, what's the next number after 0.43? Well, someone might say it's 0.44. Someone else might say it's 0.431. Maybe someone else would say it's 0.4301 because they're measuring out to tens, hundreds, thousands, 10,000s place. So I don't know what number comes next, so I can't count them. So we say that that is an uncountable or not countable infinity. Good so far? All right. So I've got two different types of random variables. There's going to be discrete random variables and there's continuous random variables. We'll deal with continuous random variables later. Right now we're going to focus on discrete random variables. Okay, so this chapter is going to focus on discrete. Next chapter we'll start bringing in continuous random variables. Okay? Now, once I've got my experiment figured out and I figured out how to write my sample space as a discrete random variable, I want to turn that into a probability distribution. Now my probability distribution has a couple of, actually three, requirements. Just three things that must be true. One, that for every random variable value, there's a probability assigned. Two, the sum of all those probabilities must add up to 1. Okay? Now we give a little tiny bit of wiggle room here because of rounding issues, because a value of 0.999 or 1.001 could be acceptable if everything was rounded, because when you round you make it a little wrong and all that kind of thing. But theoretically they should all add up to perfectly to 1. Okay? And then the last one is that the probability rules must hold. That is that every possible random variable value has to have a legit or legal probability. That is something between 0 and 1. Okay? All right, so let's take a look at an example. We'll build a probability distribution for it and see what happens. Okay? Our experiment is going to be tossing 2 coins. So our experiment is tossing 2 coins, and our random variable is going to be the variable, the random variable, that counts the number of heads. So the sample space for tossing 2 coins would be both coins land on heads, both coins, wow, that's weird. Both coins land on tails, or first coin heads, second coin tails, first coin tails, second coin heads. Okay? Our sample space contains 4 equally likely outcomes. So each of those outcomes has a probability of 1/4, 1/4, 1/4, 1/4. And each of those outcomes has a random variable assigned to it. What I mean by that is the outcome heads, heads, that has the random variable x equals 2. So then the probability that x is 2 is 1/4. Now, for the random variable, it sees ht and th as the same thing and assigns it a random variable of 1. So then the probability that that random variable is 1 would be the 1/4 from the heads tails plus the 1/4 from the tails heads to give us 1/2. And then the last possible would be tails tails, which the random variable sees as a big fat 0 because there's no heads. So then the probability that x equals 0 would just be that 1/4 probability from the tails tails. And then if I put that all together and make it into a lovely, beautiful table, I get something like this. Okay, so now just a note. Depending on who your instructor is, depending on who's writing things, sometimes you won't see this. You'll just see this. And what they're telling you is, or they're saying is that, hey, you should know that since we're talking about distributions, that having just a 2 in there means that the random variable value is 2. I find this to be a little more representative of displaying what's really going on here, but just so you know, you will sometimes see it simplified or shorthanded down to that. Okay? All right, so let's take a look at what we did down here with this table. So we created a probability distribution. Let's check to make sure it meets all 3 requirements. 1, does it cover every possible value for x? Well, x could be 0, 1, or 2. 0, 1, and 2 is covered. All right. Is the sum, number 2 up here, is the sum of the probabilities 1? Well, if I take these 3 probabilities and add them up, that does add up to 1, so we're good there. And every probability is a legitimate probability. Yeah. So we have created a probability distribution. Okay. Now, if I wanted to graph this probability distribution, I would just make a histogram, a probability histogram. So I'm going to have a vertical axis. I'm going to have a horizontal axis. My horizontal axis needs to cover the random variable. My vertical axis needs to cover the probability for that random variable. Okay? Since my highest probability is 0.5, I'm going to put 0.5 up there near the top of the graph, which means 0.25 is right there. My random variable values are 0, 1, and 2. The height of the bar for 0 must be 0.25 or 1/4. The height of the bar for 1 must be 1/2, and the height of the bar for 2 must be 1/4 again. And so we get this lovely probability histogram. And so up top, I'm going to say that this is a experiment is flipping 2 coins. X equals number of heads. So I know what's going on here. And there's my probability histogram. Now, I know what you're thinking. This was an incredibly boring experiment because we're only flipping 2 coins. All right, so what would it look like if we made it bigger and did 3 coins? All right, I'm going to start where I always start. I've got my experiment figured out, so what's my sample space? Well, my sample space could be all coins land on heads, or 2 coins land on heads and 1 tail, and there's 3 ways for that to happen by moving the tail around. And then I could get 1 head and 2 tails, so H, T, T, or any of the other possible orderings of that. So T, H, T, or T, T, H. And the last one would be tails, tails, tails. Okay? Now, since all of those outcomes are equally likely, every single one of those is going to have a probability of 1/8. Because there are 8 things in that sample space. Now, if we define our random variable to be the number of heads, then each of those outcomes will take on a random variable value. This would be a 3. That's a 2. That's a 2. That's a 2. Actually, you know what I'm going to do? I'm going to do these in different colors so they stand out. That's a 2. That's a 2. That's a 2. This would be a 1 and a 1 and a 1, and this guy would be a 0. So then when I make my distribution and I define my x's and my p of x's, I know that my x's have to have a value for 0, 1, 2, and 3. Now I know that someone, at least one person, is watching this and thinking, hey, up here you wrote them 3, 2, 1. Down here you wrote them 1, 2, 3. Does not matter. I don't know why, but my brain, and whenever I think about coins, I always think about counting heads first. And I don't know why, but when I make my distributions, I want them in numerical order. And it's not about this is the right way to do it. This is just how my brain works. So I write it out like that. Okay? All right. Now that I've got the x's in my distribution, I need the probabilities, meaning I need numbers for here, 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 and here that represent the probability of that outcome. Well, looking back at the sample space, there's only one way to get a 0. So that means we're looking at a probability of 1/8. Looking at the sample space, looks like there's 3 ways to get a 1. So that would be a probability of 3/8. Looking at the number of ways to get a 2, also 3/8. And the ways to get a 3, that's going to be 1/8. And I've got my distribution. So there's the probability distribution for the experiment. Toss 3 coins. Count the number of heads. Okay. Hey, could I turn that into a graph? Absolutely. I could make this into a lovely probability histogram. Looks like I need eighths over here on the vertical axis for my p of x's. So if I'm going to call that 1/8, I would call that 2/8. And up here I'm looking at 3/8. Okay. My horizontal needs to be my x's, so I need a 0 and a 1 and a 2 and a 3. And now I just got to draw some bars that are the proper height. Let's see, 0 is a 1/8. 1 is a 3/8. 2 is also a 3/8. And 3 is a 1/8 again. Now I shade those in because color is pretty. And there's my distribution. There's my probability histogram. So the experiment is tossing 3 coins, count the heads. Okay. And so I get this lovely probability histogram. Okay. All right, I'm going to stop this video here. We'll pick up starting down here with parameters of a probability distribution in the next video. See you then.